Om Swastiastu, Assalamualaikum warahmatullahi wabarakatuh. Salam nama budaya. And in this video I will explain about chapter 14, Metallurgy for the Non-Metallurgist. But first I want to introduce myself. My name is Putra Hutabarat with student ID number 230553010075. I'm from Mechanical Engineering Program Study, Engineering of Fakulty and Udayana University. Main referensi. Next, chapter 14, heat treatment of non-ferrous alloys. Non-ferrous alloys are heat treated to tailor their properties for a variety of purposes, including aiding in recovery by reducing internal stresses, promoting diffusion by redistributing exceeding alloying elements, promoting new recrystallized grain formation, promoting grain growth, dissolving phases, producing new phases by precipitation from solid solution, altering surface chemistry by the introduction of foreign atoms, promoting new phase formation through the introduction of ferrous ions. Next, this table 14.2 example of non-ferrous metal and alloys with a thermal quench induced or stress induced martensitic phase in non-ferrous alloys consists of two primary types: those produced by rapid quenching at thermal martensit, or those produced by applying external stress induced martensit. Some examples of each are listed in table 14.2. The internal microstructure of martensit varies greatly among the different metals and alloys, but non-ferrous martensitic transformations normally exhibit a characteristic plate-like microstructure. Next, 14.1 Recovery and recrystallization annealing. Annealing is a generic term used to denote a thermal treatment process that consists of heating a material to an temperature and holding or soaking it for a sufficient length of time at a temperature, followed by cooling at a stable rate. For steel alloys, the rate at which the alloy is cooled back down from the soak temperature is a critically important factor during the annealing cycle, and this cooling rate may also be an important factor for specific non-ferrous alloys. When annealing is performed for short periods of time or at low temperatures, the hardness of a cooled worked alloy remains relatively constant. This initial stage is referred to as recovery annealing, figure 14.1. Next, although the level of thermal activation is not sufficient to significantly affect hardness during recovery, there is some movement and rearrangement of the dislocations during the recovery stage. Thus, some properties do change during recovery annealing. For example, the electrical resistivity of an alloy is typically increased by cold working but can be recovered before annealing has a significant effect on hardness, figure 14.2. Although the level of thermal activation is not sufficient to significantly affect hardness during recovery, there is some movement and rearrangement of dislocations during the recovery stage. Thus, some properties do change during recovery annealing. For example, the electrical resistivity of an alloy is typically increased by cold working but can be recovered by annealing has a significant effect on hardness, figure 14.2. The onset on and extent of recrystallization depends on many factors such as composition, grain size, and the extent of cold work. For example, an increased amount of cold work prior to annealing lowers the recrystallization temperature, figure 14.3a. There are also in an approximate relationship between melting temperature and recrystallization temperature, figure 14.3b. Some approximately crystallization temperatures are shown in table 14.3. Okay, next 4.2 heat treatable aluminum alloys. The microstructural changes that occur during annealing are illustrated in figure 14.4. During recovery, there is a decrease in the density of deformation bands, although this effect is not prominent. When crystallization commences, small aqueous grains begin to appear in the microstructure. These continue to form and grow until the cold worker matrix in consummation, which marks the end of recrystallization period and the beginning of grain growth. Further annealing causes only an increase in grain size. Next, 14.3 cobalt alloys. Cobalt is useful in applications that make use of its magnetic properties, corrosion resistance, wear resistance, and or strength at elevated temperatures. Biomedical application is another important use. The initial biomedical applications of cobalt-based alloys were in the dental field, and early evaluations of these alloys showed excellent wear resistance, corrosion resistance, biocompatibility, and mechanical properties when used in fiber as orthopedic implants. Alloys for high temperature strength include a number of cobalt-based superalloys. Essentially, alloys of the commercially important high temperature cobalt alloys are solid solution strengthened. In the past, there were many attempts to develop edge-hardenable cobalt alloys. However, they were easily surpassed in terms of high temperature strength by the edge-hardenable nickel alloy compositions, and they never became commercially viable. High strength and general corrosion resistance are the main attributes. In particular, MP35N alloys has been shown to possess good resistance to environmental cracking in oil-filled environments. They differ in their maximum operation temperature. The MP35N alloys is usable up to 400 degrees Celsius or 750 degrees Fahrenheit, while the MP159 alloy maintains high strength to approximately 600 degrees Celsius or 1110 degrees Fahrenheit. This difference relates to the type of precipitation reaction employed. Next, 14.4 copper alloys. Copper can be hardened by solid solution alloying and by work hardening. The commonly used solid solution alloying elements listed in approximate order of increasing effectiveness are zinc, nickel, manganese, aluminum, tin, and silicon. Heat treating processes that are applied to copper and copper alloys include homogenizing, annealing, stress relieving, solution treating, precipitation, edge hardening, and quench hardening and tempering. Edge hardening copper alloys can be thermodynamically processed to provide an unique combination of strength, formability, electrical conductivity, softening resistance, and stress relaxation resistance. As an example, the solution treatment of beryllium copper alloys is performed by heating the alloy to a temperature slightly below Celsius, figure 14.7, to dissolve a maximum amount of beryllium, then rapidly quenching the material to room temperature to retain beryllium in a supersaturated solid solution. Fluctuations below the critical levels for nuclei formation do not grow. Bottom part of figure 14.88. In contrast, spinonal reaction involve a continuous or homogeneous clustering or unmixing of atoms into a two-phase structure by spontaneous growth from small composition fluctuations. Figure 14.8b. Next, the precipitation occurs in preferential crystallographic directions, providing an obvious geometric pattern in 2 or 3 directions. The chemical segregation occurs on a very small angstrom level scale and requires the use of the electron microscope to be discerned. Figure 14.9. The microstructure that develops during spinodal decomposition has a characteristic periodicity that is typically 2.5 to 10 nanometer in metallic system. Heat treatment of braces. Copper zinc alloys comprise various types of braces that have long been of great commercial importance. Copper zinc solid solution alloys are probably the most widely used copper-based alloys. They retain the good corrosion resistance and formability of copper but are considerably stronger. Zinc has an HCP crystal structure, so the solubility in copper cannot be complete. However, FCC copper is also close packed with an atomic size difference of only about 4% with zinc. Thus, solubility is extensive. Figure 14.13. Next, 14.5 magnesium alloys. The basic temper designations used to designate the various types of heat treatment for magnesium alloys include F as fabricate, O annihilate recrystallized raw products only, H strain hardened raw products only, W solution heat treated unstable temper, T2 annihilate cast products only, T3 solution heat treated and cold worked, T4 solution heat treated, T5 artificially aged only, T6 solution heat treated and artificially aged, T7 solution heat treated and stabilized, T8 solution heat treated cold worked and artificially aged, T9 solution heat treated artificially aged and cold worked, T10 artificially aged and cold worked. Precipitation occurs in many magnesium alloys, but precipitation does not always result in hardening. In many alloys, lattice coherence and lattice straining is lost early in the formation of precipitates. Some examples of significant hardening that does occur from precipitation include magnesium-aluminum alloys. Figure 14.15. Next, 14.6 nickel alloys. Nickel is an austenite former and no allotropic phase transformation occurs in nickel or the high nickel family of alloys. The alloys are austenitic from the melting temperature down to absolute zero. Nickel has a natural tendency to combine with sulfur on our oxygen. It is found in natural nickel sulfate and nickel oxide ores. In heat treating nickel or nickel alloys, it is critical to minimize exposure to sulfur in solid lubricants, grease, or gases from SO2 or H2S. Once embrittlement by sulfur occurs, the contaminated area must be removed by grinding or scraping. Nickel has a very low solubility for carbon in the solid state, so it does not readily carburize. The most common heat treatments are stress relieving in process annealing to aid in fabrication or production, full annealing to complete recrystallization, and obtain maximum softness. Solution annealing to dissolve second phases for obtaining maximum corrosion resistance, or prepare for quenching and age hardening of a supersaturated state. Quenching followed by precipitation age hardening. Age hardening of nickel-based alloys. The addition of niobium, aluminium, silicon, titanium, and certain other alloying elements to nickel and nickel alloys separately or in combination produce an appreciable response to age hardening. The effect is dependent on both chemical composition and aging temperature. It is caused by the precipitation of submicroscopic particles dragged out of the grains, which results in a marked increase in hardness and strength. Next, 14.7 Titanium alloys. Titanium and titanium alloys are heat treated in order to reduce residual stresses developed during fabrication. Stress relieving produce an optimum combination of ductility, machinability, and dimensional and structural stability. Annealing, increased strength, solution treating and aging, optimize special properties such as fracture toughness, fatigue strength, and high temperature grip strength. Microstructural features of titanium alloys. Generally, two types of alpha phase may be present in titanium alloys after heat treatment. Primary alpha, which persists through heat treatment as the remnant alpha from prior hot working of processing. Secondary alpha, also referred to as transformed beta, which is produced by transformation of beta to alpha during or after heat treatment. Primary alpha may be elongated to or aqueous depending on prior processing and heat treatment. For example, three different morphologies of primary alpha in annealed titanium are seen in the micrographs of figure 14.20. Elongated grains from prior working become more aqueous during recrystallization, annealing, and some trans. Form beta occurs after cooling from just below the beta tranches. Next, of these four treatments, the strength is not improved, but there is a sharp drop in ductility for heat treatments above 1010 degrees Celsius or 1850 degrees Fahrenheit. This drop in ductility is attributed to the formation of more acicular alpha from the transformation of P developed at the higher temperatures. However, resistance to creep deformation is improved by the formation of acicular alpha. The heat treatment of 1065 degrees Celsius or 1950 degrees Fahrenheit is above the B tranches, and rapid cooling results in a microstructure that is acicular alpha and martensite. Although this structure is known as ductile, it does provide more creep resistance. Figure 14.27. 14.8 Other non-ferrous alloys. Heat treatable silver alloys. The precious metals, including silver, behave somewhat similar to copper and nickel. The most important silver alloys are the silver-copper type. Copper is added to increase the hardness and strength of silver, while its effect of the electrical conductivity is small compared to that of other additions. Coin silver containing 10% Cu is the most common alloy. Fine silver is used for electrical contact. Tableware is usually made of sterling silver or standard silver having 7.5%. Heat treatable gold alloys. The gold alloys, which find application in the jewelry setting, trade and indented dry, generally contain silver and copper, and sometimes zinc, nickel, platinum, and palladium. The properties of considerable number of test alloys are altered by different phase change. The copper-bearing gold alloys are characterized by the occurrence of at least two transformations in the solid state. One phase AuCu itself is not hard and brittle, but the transformation of the disordered solid solution at temperatures below 500 degrees Celsius or 900 degrees Fahrenheit into this phase results in a brittle condition. A number of gold alloys containing copper therefore have to be quenched from temperatures above 500 degrees Celsius or 900 degrees Fahrenheit in order to be workable. Pure tin exceeds in two modifications and the transformation temperature is below room temperature. This phase change is accompanied by a complete decomposition of the tin, which starts from one or several points in a section and slowly spreads. Very pure tin is particularly susceptible to this tin paste, while small addition or 0.1% of bismuth or antimony prevent this integration. Okay, I think that's I can explain about chapter 14. If there are an error in reading, please forgive me. And Om Swastiastu, Assalamualaikum warahmatullahi wabarakatuh, Salam Nama Budaya, and thank you for watching my video.